Hey, what's up, and welcome back to the AI Concepts and Coding from Scratch. In this video, you will learn how to code a transformer from scratch using PyTorch. If you want to learn Python, data science, machine learning, and GenAI, subscribe my YouTube channel. What are transformers? A transformer model is a neural network that's learn the context of sequential data and generate new data out of it. See, sequential data. To put it simply, a transformer is a type of artificial intelligence model that's learned to understand and generate human-like text by analyzing pattern in large amount of text data. Transformer are first developed to solve the sequence translation or neural machine translations, which means they are meant to solve any task that transform an input sequence to an output sequence. So this is why they are called transformers. If I expand this transformer block, we have the encoder and the decoder. That's mean transformer is nothing but the combinations of the encoder and the decoder. It's nothing but taking one input text, let's say how are you in English sentence, and after that it will combine them into inside the encoder and the decoder, process them, and after that it will give me one translated language. It can be the German, it can be the French, it can be the Bangla, or it can be the Hindi. If I expand this encoder and the decoder in the sections, we have the multiple number of encoder. Encoder 1, encoder 2, encoder 3, and up to end. In the paper called Attention is All You Need, the mention the size of the encoder and decoder should be the 6. Same thing for the decoder, starting from 1, 2, 3, and number of n. And also in the encoder and the decoder, they're using one kind of mechanisms called the multi-hat attentions, also started from the self attentions. And see, we have some of the data is passing from the encoder to the decoder. You can see encoder to the decoder, and all of the output should be passing to the next layer as the input to the encoder. Same thing for the decoder. So now what I can do is simply going to coding this transformer and with the theory explanations. Okay, if you break down the ChatGPT or the Llama, you can get here the architecture of the transformer. So that's why transformer is right now the most and powerful things in the case of large language model. Now let's start the coding part and go in our Jupyter notebook. In order to coding a transformer from scratch, you're going to using here the popular library called the PyTorch. So first I'm going to import it here. Let's say import here the PyTorch. Let's say torch. Make sure that you install this PyTorch library in your system. Then I'm going to importing here torch. Let's say torch.nnSNN. It's called the neural network library or the module. Then I'm going to importing here the optim from the torch so that you can do the optimization while training process. So I'm going to import it. Let's import torch.optim. I'm going to using it as a optim for the optimizations. Then I'm going to using here these utils to handling the data. So I'm going to import torch.utils.data as data. Then I'm going to importing here the math so that we can also do some mathematical operations while building here our transformer. And for this case, you're going to using here one popular paper that's called Attention is All You Need. Then I'm going to importing here copy so that you can copy some of the complex objects. Okay. Now I'm simply going to running this out. And after that, we're going to go on our paper that's called transformer. Attention is all you need. This is the paper called Attention is All You Need, which on change the world in the form of natural language processing as well as the GPT, the large language model. And after that, ChatGPT is coming to the pictures. And this paper is built by the Google Brain researcher, Google Brain and the Google researcher team. And if I go down, we have one structure of the transformer, just called the model architecture. And in the model architecture, you can see here it will take one input and as well as it will giving me some output. See, this is called the transformer architectures. In the transformer architecture, it having two blocks. One is called the encoder, another one is called the decoder. In the encoder, it will using one important technique called the multi-hat attentions. And also you can see here you use here the feed forward neural network, as well as they use here one mux multi-hat attentions, and also introduce one new types of encoding technique called the positional encoding. Okay, so this block is called the encoder block, this is called the decoder block. Okay, now if I go down, it is nothing but called the encoder and the decoder stack. That's mean transformer is nothing but a combinations of the encoder and decoder stack. Okay, you can see here they're also using here the and cross. That's been number of encoder and number of decoder. In the paper they mentioned number is called a 6. You can see number is 6, called identical layer. And also one more important variable is called the d model, that's called dimension of the model, is called 512. Okay, make sure that while you do the coding part you need to also remember this variable name. And in the decoder part, you can see here they're also using here n equal to 6. I mean, number of actually a decoder. Okay. And if I go down, you can see here the most avoided thing, that's called the attentions. Now you can see here they're using here the multi-hat attention. But before that, you need to know that what is the self-hat attention, like, or the self-attentions. Okay. And they're also using here a formula called the scale dot product attention. You need to also learn about that. Okay. Now I am simply going to go down and see the formula of the scale dot product attentions, also called the self attentions, and it will using here as softmax activation functions, which one having the q, just called the query, just like the Python dictionary, key and the value. Okay, and after that they're using here the dk. Okay, this is not about the dimension of the k vectors like that. Okay, so they're also using here the formula for the multi-hat attentions. And if I go down, you can see here this is not about the formula of the multi-hat attentions. Now we need to learn that one more thing. See, the transformer architecture is nothing but is coming from the RNN, also called the recurrent neural network. Now the question is, why not RNN, and why should you need to using the transformer? Transformer is nothing but used for the language translations or the text summarizations. Okay, just like sequence to sequence model. Now yes, we can do it using RNN, but why the transformer is introduced? Now, what is the RNN, also called the recurrent neural network? Recurrent neural network can remember the important things about the input they receive, okay, which allows them to be very precise in predicting which one is coming next. That's mean yes, this one also taking in the participate in the language translation as well. But the problem is this RNN taking the data in the sequential manner. Sequential data like the time series, like the speech, text, or the financial data, even audio and the video. Now the question is, yes, we have the RNN. So why the transform is coming to the pictures? Because of RNN take the data in the sequential manner in some kind of time step. But in the transformer, you can pass the data in the parallelized way. That's mean in transformer, the training time is less rather than the RNN. So that's why the RNN is dropped and transformer is coming into the pictures, and you got here the most awaited large language model called the ChatGPT. Now, what is the self-attention? So this is the formula of the self-attention that you can see in the paper as well. So self-attentions allow the model to relate it what to each other. That means you can pass the data in a parallelized way. See, we have one nothing but one matrix, which one having one word called I love you in every inverse. In the matrix, you can see here for the each of the word, it having some positional embedding value. Okay, and if I join them, we have got one at the summations. Okay, and this is the formula for that. This is called the q and the k and the b. Now the question is, sir, what is the q, k, and b in the self attentions? So why query, key, and the values? So the internet say that this term come from the database terminology or the Python like dictionary. In the Python like dictionary, we have the key and value pair, just like the Python dictionary that you can see on here. So in the dictionary, let's say I am going to keeping here one query called the love. Now based on the love, it will try to creating here some kind of arrow. Now using this love, we can actually demonstrate here the romantic, because love always be romantic, and the value is called the Titanic. And romantic and the comedy is nothing but actually related to the love. So that's why you actually using the query, key, and the value in our self attentions. In here, you can see here when actually using here this query terminology. In here, you can see here some kind of deep of the purple color. That's mean these two values correlated to this love. So this is how our transformer actually work as a key, value, and the pair. In the multi-head attention, this is really important role. It's played an important role, the query, keys, and value, because those are data important. It is passed to our scale dot product. Now, how to compute these self attentions? So just you need to passing here with this formula, and after that you can join with, I mean, cross multiply with this b, I mean value, and after that you can get the attentions. Okay, each doing the matrix capture not only the meaning given by the embedding or the position in the sentence represented by the positional encoding. Okay, when you're actually deploying these multi-hat attentions, okay, after that we will discussing about this positional encoding. What is the positional encoding and why it's important? Because we see that in the NLP tasks, we're using the what to back or the bag of word or the what embedding. So now what is the positional encoding and why it is actually introduced? This is the formula for this multi-hat attention that we see in the paper. So this is the formula for the self-hat attention or the scale dot product that you can say. And the multi-hat attention is nothing but having the multiple number hat. The number of hat is nothing but the six in this paper. They mentioned that. And this is nothing but Q, WQ, and W key and WB is nothing but one kind of vectors that you need to actually creating on that while passing to in our multi-hat attentions. And WO is nothing but called the output transformations on that. So while you do the coding part, then you can understand this thing very well. Now let's see the architecture and our workflow of the multi-hat attentions. In the multi-hat attention, let's say this is our encoder block and we have the multi-hat attentions and we have some kind of variable. We need to actually remember this thing. Sequence is nothing but the sequence of length of the word. Let's say I'm going to passing here a sentence called I love you in every universe. This is one sequence length of the word. And after the D model is nothing but size of the embedding vector. And head, H is nothing but the number of head. And DK and DB is nothing but D model by H. See, DK or DB is nothing but D model by H. Why we're discussing on here? So you have an input called sequence by D model, and D model is nothing but called 512. So sequence length can be 5,000 or 10,000, whatever else. It's depend on your machines. Then we have the three matrix called query, key, and the value, which one is nothing but sequence and D model. See, sequence and D model. And after that, we're going to combine them with these one transformations. We have in W, okay? We have in WQ, and we have the WK, we have the WB. See, this is called the sequence into D model. Then you're going to make a D model cross D model. And this is nothing but one linear layer. See, this is nothing but one linear layer. That's you need to creating here one linear layer for the WQ, WK, and the WB. And after that, you need to do the matrix multiplication. And after that, you can got here the Q prime, which one is nothing but sequence into D model. See, in the matrix multiplication, if I actually crossing this one and this one, these two term will be crossed. These two term D model will cross, and the length or the size of the matrix should be sequenced into D model. That means if I'm going to crossing this with this WQ, this Q sharp or Q prime obviously but same. That means this is nothing but is representing on here. But when I do go on here and actually divide them into multiple number of hat with our multiple number of hat, we have to divide them. That's why DK is nothing but this one is nothing but a single face of the hat, single face of the hat. And D model is nothing but our full model, this one. We're dividing this with the number of hat as well as the sequence, okay, as well as the sequence. And after that we have the number of head. Let's say we have the four head right now in here, and after that we're simply going to combine them into our head. Our head is nothing but called sequence of H cross DK, okay. And after that we're going to combine them with our output transformations, and we got here our multi-hat attentions. You can see here this is the attention visualizations that you can see the query key in the below. You can see here this model is actually related to this one. It will try to getting this one. So why this multi-hat attention is important to the language transformations, I mean language translations. Let's assume that one sentence in Bangla, এখানে প্রস্রাব করিবেন না, করিলে এত টাকা জরিমানা দিতে হবে তোমাকে. Let's say I just give it a comma into after the na, before the na. That's mean এখানে প্রস্রাব করিবেন না করিলে এত টাকা জরিমানা দিতে হবে. Because see, the comma is nothing but giving one important roles in this language translation, because it will changing the whole sentence of that just for the one comma. That's why in the language translations, this uh, sequence is important. Sequence should be matter. It can be the money bank or the river bank. Money bank and the river bank have different scenario. Okay, money bank is nothing but for the bank of the money, and river bank is the bank of the river. Both words have some different meaning. So that's why this multi-hat attention is coming into the picture. I understand. I actually teach you in the Bangla as well as in the English as well. Okay. Now in the decoder part, we having another one called the mux multi-hat attentions. Now the question is why in the output mux multi-hat attention is coming into the picture? Just because of creating here some kind of marks in the diagonal format, so that our model cannot see our next word. Okay, so that our model cannot see in the next word that is coming on here. Okay, so that's why this mux multi-hydration is coming into the outputter model, I mean, and decoder, so that our model cannot see the a value. Otherwise, our model should be the overfitted. Okay, if the model see all the data, obviously it should be overfitted. So that's why all the value above the diagonal are replacing with the empty before applying the softmax, which you replace them with the zero. It's called the max multi-hydration because you're going to creating here this multi-hydrations in a single code. That's why you need to also understand this thing. Okay. So now we're simply going to quote here our multi-hat attentions. Now let's go on our Jupyter notebook. Now let's create here a class called the multi-hat attentions. Let's say class multi-hat attention. Let's say attention, which I'm taking one nn dot module. Okay, let's say module, and after that you need to creating here the def of init. You need to passing it to our initializations, and then inside that you can passing here the self, and then you need to passing here the d model and the number of hat that you see in the paper. Okay, number of hats, and then you're simply going to using the super keyword. Let's say super, and you can using here this multi-hat attentions, and you can passing here the cell, and then you're going to using here underscore init and underscore this one. Okay, now we need to initialize the dimension of the d model and the number of hat. But before that, if we see in the multi-hat attention, we will divide this d model with the number of hat. That's mean if my data or if my data, I'm going to divide here one odd number to the odd number, that's mean I can get the value. Now let's say I'm going to divide here one odd number to the even number, I don't get any values. So I need to using here an method so that I can checking that if the hat number of hat and the d model is coming, it be visible or not. Okay, because we need to divide them the d model, because number of hat is nothing but 6. Let's say user गलती से दे दिया पर 7 दे दिया, तो एरर तो आएगा ना भाई, काम नहीं करेगा मल्टी हैट attentions because it should be the divisibles. Now it's simply going to divisible by d model of the number of hat. Let's say number of hats. Okay, it should be equal to 0, and then after that you can giving here, let's say d model, okay, must be, because this assert is giving here some assertion error, divisible, okay, by number of hats. That's the number of hats, like that. Okay, it will give me some assertion error if we got any error on here. Let's take in some shell, it will be better for me. And after that, I'm simply going to initialize the dimension of the d model and the number of hat. So I can using a self dot d underscore model is equal to d model. That's a d model. And then I'm going to using a self dot number of hats equal to number of hats. Okay, number of hats. Then we see one important one that's called the dimension for the each of the hat key, query, and the value in our pictures. We need to divide them with the number of hat. Okay, so we can make it as a dk. Okay, dk is nothing but divide of the d model by number of hat. Okay, so now I'm going to be passing here the d model, and we're going to divide them with the number of hat. That's the number of hats. This is called the self of dk. Now this is taking the d model and the number of hat, the multi-hat attention. Then this is called the initialization of the dimensions. Now I'm going to creating here our linear layer for the transforming the input. So those are the linear layer that's called the WQ or WK and the WB. And those data is coming from as the input. So we don't need to mention it here. It is coming from the positional encoding. So we don't need to carry about them. We need to just creating here this QQ, QK, and the QB. This is nothing but called D model cause D model of the sequential layer. So you can go on here and going to creating this out as a self dot, you can passing here W of the K, that's a Q, sorry. This is called the Q, W matrix for the Q. This is called linear layer. So you can using here nn dot linear, that's a linear, and which one taking on D model and the D model. And then to copy this out, you know, to using it here for the 4 times. Okay, why? First one for the Q, and second we have the key, we have the value, as well as we have one output. Let's go on here in the slide that you can see. Okay, in the slide you can see here we having one output vector as well. Okay, now we actually do it for the query transformations, the key transformations, the value transformations, as well as the output transformations. Now what I can do is simply going to creating here our first layer. It's called the scale dot product. So for that, you're going to creating here functions. Now let's go on the paper and see that what is the scale dot product attentions. In the paper, if I go down, you can see here we have an actually things called the scale dot product attentions, which on taking one matrix multiplication of the q and the k, this pass into the scale, and also using here marks is optional. That means if we have the using the multi-hat attentions, I mean max multi-hat attention to using this marks as well, then you're going to passing to inside on softmax activation functions, and after that you're going to multiply with the b, I mean the value. This is called a scale dot product. Now we need to getting this one, but if I see the complete architecture of the multi-hat attention, this is nothing but taking the b, k, and the q, which one is nothing but a linear layer, and after that it will passing to the scale dot product of the number of hat, and it will concatenate it and passing to one linear layer. This is nothing but one summary of the multi-hat attentions. So going to follow this on and try to creating here this linear layer. We are already creating this out, and now we're going to creating here this scale dot product using this formula. Okay, so now let's creating here our functions. Let's call the scale dot product attention. Let's say scaled dot product attention. Let's say attention, which are taking the self, the query, key, and the value, and the marks itself. Okay, let's making marks as a noun because it's optional. It should be a scale dot product. Now, if I go on the paper that you can see on here to go back, and you can see here this is called the scale dot product attentions, and this is called the multi-hat attentions. And in the scale dot product attention, you can see here it will take in the q and the k, and to do the multiplication we have on a scale, and we have in the max is nothing but optional, and also the softmax you can see here. Okay, now we're simply going to do the matrix multiplication, and where k is nothing but our transpose matrix. For that, if I see the formula on here, if I go down, if I see the formula, you can see here q and the k, and k is nothing but the transpose of that. And after that, we need to divide them with the square root of the dk. Okay, dk is nothing but called d model by numbers of hat, and also combine them with this b. Okay, let's go on here again, and now we're simply going to creating here the attention score. Let's say this is called the attention score. Let's say attention score, and then we're going to using here torch dot matrix multiplication. You can using here mat mul, and inside that you can passing here the query and the key of the transpose. Let's say transpose, and inside that you can passing here the -2 and the -1. It will do the transpose of that, and after that you need to divide them with the math.squirt. Let's say math.sqrt, and inside that you're going to be passing here the self of dk. Okay, self dot d underscore k that we see in the formula. Okay, now after that what I can do, we need to apply the marks. If the apply marks is provided, then we need to also giving the formula for here. Let's say if the marks is not none. Okay, it's not like that, it's not none, I mean marks is applied, then we can simply going to preventing simply going to creating here some of the marks which are having nothing but the fill up of the empty, I mean infinite. If I go on here, you can see here this marks is nothing but replaced with this infinity number in here. This is nothing but creating some padding of that in the diagonal format. This is called the generated marks. Now I am simply going to apply it in our attention score. Let's say attention score. Okay, attention scores, and you're going to using here attention score. Let's say attention score, attention underscore scores, and then you're going to using here marks field. Okay, let's say marks field. Okay, it should be marks field, and if the marks is equal to 0, let's say marks is equal to 0, then you can give it here of the infinity number. Let's say -1 E9. This is called the infinite. Okay, now after that what I can do is simply going to apply here the softmax that we see in the formula. Okay, while you do the coding, make sure that your paper should be in front of you so that you can actually get some clear clarifications about the code. Okay, then after that we have the attention probability. That's attention probability because we're going to passing it inside the softmax activation functions. So we're going to using here the non-linearity on here. So you're going to using here torch dot softmax. We're going to using here soft max, and inside that I'm going to passing here the attention score. That's the attention score, and then I'm going to passing here the dimension is nothing but called -1. Okay, and after that what I can do is simply going to do the multiplication with the value. So just nothing but my output. So output is equal to torch dot mat mul, and inside that you can passing here the attention probability. Let's say probability, and you're going to passing here the value for here. Okay, and after that you're going to return here the output. Let's say return here the output. Okay, it is the output. Now our scale dot product is also complete. Okay, now we're simply going to split the hat. We need to split the hat. If I go on here, if I go on here, you can see here after that, into split the hat. You can see it have the 4 hat on here. To split the hat, you can see hat number 1, hat number 2, hat number 3, hat number 4, like that. We to also do the splitting, hat of the splitting. So what I can do is simply going to reshape them. See why reshape them? Because see, we have the sequence length in the D model. Sequence length in the D model. When actually combining them, we got the sequence length in the D model, and after that we have the batch size, because we're going to pass this data in the formal batch size. So we have the sequence length, number of head, and the decay. You can see on here in decay. If I zoom, you can see here sequence length, number of head, and the dB is nothing but the decay. Okay, dB is nothing but the decay. Okay, if I see on here decay. So what I can do is simply going to creating this out in the form of batch size. Okay, so because we're going to pass the data in the form of the batch size, so we can go on the code and we're simply going to creating the functions called the split hat. So I'm going to go on here and that's a def. It should be better. You can remove the space from here because it's not necessary at all. So def, let's split underscore hat, and then you're going to passing a self comma x, and then you need to reshaping the data that is coming from the x. That's the x dot size, and this x dot size nothing but giving here the batch size, sequence length, and the D model, because you want see here, see sequence length and the D model, sequence length D model, sequence length D model. See, okay. So we have also adding here a batch. So let's say batch size, say batch size, and you have the sequence length, and then you have the D model. See how you split the hat. Okay, so we have this one batch size, okay, BATCS batch size, and then we need to actually reshaping them using this formula that's called extra view. So you can using an extra view in Python. So you can also reshaping it in the same size of matrix in another kind of matrix. We can passing it to here. We can passing here the batch size. Let's say batch size, and then you're going to passing here batch size. थोड़ा आस्ते जाना होगा मुझे. We have the sequence length, sequence underscore length. Then we have the number of head. That's a self dot number of head that you already initialize on here. You can see number of head and the self dot decay. Okay, self dot decay. This is nothing but our the split of the head. That how can you split the head, and you also do the transformation of that. Let's say transpose of the 1, 2. Okay, because the matrix should be the transposes in this shape to the this 4-dimensional shape. Again, go on here and see. You can see that how can actually split the head with by sequence length. Okay, we have this formula sequence length, h, and the decay. Okay, decay is nothing but dB, as well as you can see. Decay is nothing but the dB. Okay, that you can see on here. So now what I can do is split the head. Now I need to combine the head. You can see to combine the head after that. Okay, so after combining the head, we have the batch size, h, sequence length, the D model of our x size. Now we need to combine them in the same size of that. See, same size we have the head on that. Now we're defining here the functions called the combine the head. Now let's creating here the functions called the combine head. Let's say def combine head, so that you can combine the head in the same size of the vector. That's the self of the x. And now after that, what we can do, we have the x dot size, and now this x dot size is combining into batch size, sequence length, and the number of head as well. Now this combine of the size is nothing but called batch size. Let's see the batch size. Then we have the number of head. Then you have the sequence length, because see why sequence LNGTA sequence length and the decay. See why? Because see, we are using the transports. It will transport this whole matrix after that. Batch size is nothing but is go on here, and this number of head is coming into this side, and this sequence length is coming in this side. So that's why Hoyne actually expand this and you have to actually start in this kind of way, because this is mentioned in the paper. Now we're simply going to combine them with the transport matrix. You can do the transformations of that, and after that you can do the contiguous, and you can using this view method. So you can using a return of the x dot transpose, and you can using here 1, 2, because we're using his 1, 2 as well. You're using it here, and then you can using here contiguous. That's a ZU. Okay, it should be ZUOS. Okay, ZOUS contiguous, and after that you can using here the view method. Okay, that is used in the split head as well. So you're going to passing here the batch size we're going to passing here the sequence length and the self of D model. Okay, self dot D underscore model. Okay, while you're combining our the same thing is coming on here. Okay, when splitting the head, we need to have the batch size, sequence length, number of head, and the decay. And after that, when you combine them in the same head, we need to making in the batch size, sequence length, and the D model that we see on here. Okay, before that, now we're simply going to creating here the forward method so that you can combine them. So that you can apply here the back propagation as well. We have initialized all of the variables, all of the of the structure of the transformer of the multi-head attentions. Now we can combine them and try to creating here our forward method. Okay, you can see here in the queue it will take in this QW and as well as it will take in the split head. Now we're going to pass in through inside our split head as well as going to pass in through inside this QW. Then we can got this Q. Okay, and this Q is nothing but passing is a parameter as well. Now you can initialize this one. Let's say Q equal to self dot split head. So you can using here split head, and inside that you can passing here self dot W underscore Q. It should be W underscore Q, and inside that you can passing here the Q is coming from here. Okay, because you need to also do the transformation on here. And after that, what I can do is simply going to do the same thing for the K and as well as the B. So it should be the K. So capital of K, capital of K, capital of B, capital of B. And after that, you need to making this convert into the small letter K and the small letter B itself. Okay, now define here the Q, K, and B. And after that, you're simply going to perform the scale dot product that you actually mentioned on here. So I'm going to copy this function that's called a scale dot product attention. And after that, inside that, I'm going to pass in here my Q, that's my Q, key, and the value. And as well as I need to pass in here the marks. So this is nothing but my attention output. Let's say attention, and this is called output. Now we are going to binding this output to the W0 that you mentioned on here. That's our output, right? If I go on the slide, then you can see we need to bind them with the output number 0 with the matrix multiplications. Okay, so what I can do is simply going to go on here, and after that you can simply going to do his output, and output is nothing but called self dot W underscore O, and inside that you can pass in here self dot, we need to pass in here the combine head because you're going to combine the head. After that we're simply going to pass it inside the WGO. Okay, so let's say combine head, and inside that you can pass in here the attention output. Let's say attention underscore output. That's it. Now that's our output. We're simply going to return in this out. Okay, so let's say return here the output. So that's our multi-hat attention. Okay, having some problem on here. We need to check in this out, assertion error. So if the assertion of the D model is nothing but equal to 0, and to giving here a comma itself. Okay, again return the output in the line number 14, return outside the functions. Okay, into making return outside the functions. Okay, it should be outside the function. That's why this problem, to make it to the inside of the functions. Now let's see. So that's our output. That's our multi-hat attentions. In the summary, the multi-hat attention class encapsulates the multi-hat attentions mechanism commonly used in the transformer model, and it takes care of splitting the input into head, and then it will apply it to your multi-hat attention, and after that it will combining the result of that, and then we're simply going to capture the various relationship in the input data at a different scale. It can be the language translations. Now we simply going to creating here another class for the position wise feed forward network. If I go on the paper and if I go down, you have one the 3.3. It's called the position wise feed forward network, which one is nothing but taking one ReLU activation function, which one having the weight and the biases as well. It having the weight number 1 and the bias number 1, weight number 2 and the bias number 2 on here. You can see on here. In addition to attention sublayer, each of the layer in our encoder and decoder contains a fully connected feed forward network. See, feed forward network, which is applied to each position separately and identically. These consist of two linear transformations with a ReLU activation functions in between. Now we're simply going to define these functions called the position wise feed forward network. So I'm going to go on the code, And then I'm going to creating here a class for the position wise feed forward network. Let's say class position position wise, let's say WISE feed forward. Okay, let's say feed forward, which one taking inheriting here the nn dot module itself. And then we're going to using here self. Okay, okay, self, not self, actually def. We're going to using here init, and inside that you can passing here the self, the D model, and as well as we have the DFF. This is nothing but for the hidden layer. And the output value is input value is nothing but called 2048 in the hidden layer. Okay. And D model is passing through in our positions wise feed forward network. Now we have the two fully connected layer, but before that it also using the super keyword and passing here the position wise feed forward network, and you're going to passing here the self, and then I'm going to using here underscore init underscore this one. Okay, so it should be underscore sorry. And then we are going to using here, we need to initialize here our two fully connected layer. So let's say self dot fully connected layer 1 is equal to nn dot linear, because it is nothing but using here the linear transformations that it mentioned in the paper. So I'm going to passing here which one taking the D model. Okay, D model, the D model, and it will taking the DFF as an input. Okay, and the second layer it will take in the output of this one, because if I see the formula of that, if I see the formula of that, you can see here it will taking one ReLU activation functions of the first one, and second one is multiply with them. Okay, that means this data D model should be passing through inside our DFF. You can say DFF, and DFF is nothing but 2048. If you're reading this one, another way to describing this one is two convolutions with kernel size 1. The dimensionality of the input output is D model of the 512, and the inner layer has a dimensionality of DFF is called the 2048. Now we're simply going to go on here and try to get in this one, our first layer, and our second layer is nothing but called FC2 is equal to nn dot linear, and inside that you can passing here the data from is coming from DFF to the D model. Okay, this is called the initialization part. See, while you are creating any class in the pytorch or any kind of object oriented programming language, first you need to do the initializations, and after that you can apply here the forward method. In the forward method you can apply here all of the technique, just like the back propagations or any kind of calculations. Then after that we have the ReLU activation function. Let's say self.ReLU, and then we're going to using here ReLU. Okay, this is called the initialization. I am going to make it here. Let's say this is called the initialization technique. Okay, let's say initialization. Okay, this is the initialization technique that you have to actually use it in every of the code. So we can also give it to here initializations. Okay, initialize the dimension. Let's say initialize dimension. Let's say dimension like that. Or it should be dimension like that. Okay, so this is the initialization technique. Okay, now what I can do is simply go into calling our forward method and combine all of them. So you can using here def forward, and inside that you can passing here the self and the x. So we're going to using here returning here the fully connected layer of the two. So we can, let's say self dot fc2, and inside this fc2 we're going to apply here the self dot ReLU. See, self dot ReLU, and inside that you can using here self dot fc1 of x. Now see, first we are going to doing this one. We're going to passing this fully connected layer of the one to our ReLU activation functions, and after that we can cross it with our fully connected layer 2 that is mentioned in our paper. If I see on that, we having the ReLU activation functions for the fully connected layer of the one with having the x, you can see x dot, and then we having the cross with the another of the fully connected layer, I mean the number 2. Okay, now this is called our positions wise feed forward network. Now next, let's move on our next topic called the embedding and the softmax. I mean embedding. So if I go up in our architecture, you can see here it is using here a different kind of encoding technique that's called the positional encoding. Positional encoding, it means we have the encoding as well as having some positions. Let's say taking an example, money bank and river bank. Okay, because both have both word are same and which one having the bank, but the terms and the translation is the different. So that's why positional encoding is coming to the picture so that it can take in the position. Let's say I'm going to writing a sentence that's called, let's say, how are you? Let's say, how are you? That's mean tum kaise ho? Like that. Let's say I'm going to making this one, you are how? You are how? This what don't have any significant. Okay? Because see the what of the position is important on here. The position of the word is important. Let's say I'm going to typing here another, let's say money bank. Let's say money bank. And also let's say river bank. See those what have also different significant. Money bank का मतलब है money, पैसा का, और river bank का मतलब है घाट का और नदी का, बस खत्म. So that's why the positional encoding is coming to the picture so that you can remember the position of the each sentence so that it will give me the response for that. Let's say ये क्या होगा, तुम कैसे हो? Let's say तुम कैसे हो? Like that, right? So see तुम कैसे हो इसका मतलब है क्या, it's nothing but the sequence of that. Now let's say I'm going to making this one so it's not embedded, so that's why sequence is important on here. That's why the positional encoding is coming to pictures. It's better, let's go on a slide and see this out. So in the positional encoding, it will calculate the value based on two periodic methods called the sine and the cos. Okay, using the sine and the cos, we can calculate the periodic motion of the value, as well as after completing this one, we can getting some periodic value in the form of contiguous. If I see the formula of that, you can see here this is the formula of the positional encoding. The formula is called sine position of the 10,000 of the 2I model. And if I taking a sentence as example, I love you, like that, then it will taking this sign of the periodic motions in the form of the uh, odd number. In the odd positions, it will actually taking this one sign in the periodic manner, and in the cos, it will taking the even position from here. And using this one, you can calculate the positional encoding. I am not going to do the deep of the positional encoding. You can go on the Google and search for that, because I am going to do the coding part, and that's why I need to focusing on these scenario that's called the role of the mathematical formula. In the mathematical formula, it will taking one positions, and based on the position, I need to taking it break it down. That's when in some position the value should be calculated with the sign. In the even positions, the even position the calculate should be in the using the cos. So that's why, and even though we know that the sine and the cos is nothing but the periodic types of formula. Okay, so that's why the positional encoding is used in the transformer, because you need to using the periodic motions as well as unbounded, bounded, as well as the contiguous value. Now you can simply go into creating the class for the positional encoding. If you don't need to actually learn more about that, you can go on the Google and search for that. What is the positional encoding for that? Otherwise, comment down below so that I can creating here one complete video and mathematics behind the positional encoding. So I'm simply going to creating here one class called class positional encoding, and inside that I'm going to using here another dot module. Now after that, okay, should be position, okay, positional encoding, and then I'm going to using the same thing. Let's say def in it, because I need to do the same thing again and again in it, and inside that I'm going to passing here the self d model and the max of the sequence. See, max sequence. So max sequence length is nothing but my input sequence length of our sentence. Let's say I'm going to do the translations using the transformer. So I need to have one source text as well as we have one target text. So for that we have also one sequence length to calculate it based on this encoding, because the encoding should be calculated based on the sequence length. Okay, if you know the basics of the RNN as well. Okay, now we simply going to creating here the super. So let's say super, and you're going to passing here the positional encoding. Okay, let's say positional encoding, and inside there I'm going to passing here the self, and then I'm going to using here underscore init. Let's say init it like that. Now we need to do the initializations. So what I can do, first we're going to divide this thing into some fractional moment, I mean deep term. And if I go on that, if I see the formula of this positional wise embedding, positional embedding, you can see here P is nothing but called the position of the 2i sign, and it having some deep term. So you can do the deep term and you also divide them with the position. So what I can do, I actually minimize this thing, in a simpler manner. Let's try to do the coding part that I'm going to discuss about that. So you have the PE. So how can we calculate the PE? Because in the positional encoding, we have all of the values should be filled up with the zeros. If I see the slide again, in the slide you can see here some of the all of the value is actually filled up with the zeros, with the max length and the D model. Okay. So after that, we simply going to calculate the position of the each periodic method. Now you're going to using the torch dot zeros. That's the torch dot zeros, and you're going to passing here the max sequence length, as well as I'm going to using here the D model. And then after that, what I can do is simply going to taking the positions. That's the position is equal to torch.arrange, and inside that you can passing a 0 to the max of the sequence length, and then you're going to using as D type is nothing but called the floating point number from the torch. Let's say torch dot float, and then I'm going to make it unsequence. Let's say unsequence. Let's say SQUEEGE unsequence, and then after that I'm going to calculate the deep term in a summary manner or the shortcut manner. Let's try to do the deep term. That's our deep term. So our deep term have torch dot exp. Okay, and after that you can using a torch dot arrange. Let's say torch dot arrange, because this is really quite big task, the positional encoding. So I can't actually cover this out in a simple times of video. Just I'm going to write it down to the code, but later on when you go to the Google and search for that, you can learn about that. Okay, I'm going to passing here the D model. Just you following here the actually, or just following here the formula that you can see on here. Formula, you can see D model, and you're going to using it to the explanations and D model, and after that you're going to give it here 2i, and after that you're going to using here the floating point number. Let's say float, and then you're going to combine them, and you're going to using here the -1. Let's say math dot log of the 10,000. Let's say 10,000. Okay, 10,000, and after that you can divide them with the D model. Let's say D model. So that's our that's our deep term. Okay, now you have the positions, and as well as you have the deep term. Now you're going to apply it the sine and the cosine, I mean our periodic functions. So for the odd, for the event, sorry, we're going to using here the cos, and for the odd we're going to using here the sine. Okay, so that's the PE, and you're going to using here this one, and it should be the 0 to 2. It's starting on the event, and then I'm going to using her torch dot, and I'm going to using her sign, and inside that you can passing here the position clause deep term. Okay, position called deep term. That's actually hitting on here position on the deep term. If you see the formula again मैं actually दिखा रहा हूँ क्योंकि बहुत confusable है ना. Sign position divided by this term. Okay, we simplify this one. Okay, deep term. Then after that we have the positions of the next one. Let's say it should be the 0, let's say 1 to 2 2. Okay, this is nothing but for the the even one. Okay, so let's say torch dot cough, and inside that you can passing here the position into the deep term. Okay, let's say deep term. Okay, so this is for the odd term. Let's say odd term, sorry, it should be the odd term, and then we're simply going to, okay, it should be the odd term, and this is the even term for the sign on. Okay, you need to using here this hashtag, and also using the hashtag as well on here. Okay, now we divide this, and we're going to calculate this part. Now we're simply going to register it in our buffer, so we can using here self dot register buffer, because this is a trainable parameter. So you can using here the register buffer, and inside that you can give it here on buffer name. That's our positional encoding, and we're going to passing here the pe dot unsequence. That's on sequence and of the 0. Okay, and then after that what I can do is simply going to actually create here the forward method. So you can using here, let's say def forward. It should be the after that, let's say def forward, and then inside that you can passing here the self comma x. Okay, and after that what I can do is simply going to using here the return of x plus of the self of pe of the all of the things. Okay, so you can using here comma all of the row of the comma from the x2 dot size. Okay, that's what. Okay, and to passing here one as well. Okay, see, we're creating here the P and we're creating the positions as well as we're creating here the deep term. And after that, for the event term, we're going to calculate this one using sine. And for the odd term, we calculate the cos. Okay. Now this is our positional encoding. Now we need to combine them at all and creating here our encoder and the decoder layer. Now I am simply going to running this out, and after that we got some error. So it should be one comma, and now it's gone. Now we're simply going to creating here our encoder layer. Okay, let's go on the paper and architecture of the transformer. Well, so you already defined the basic building block, just like the multi-hat attentions, the position-wise feed-forward network, and the positional encoding. Now we're simply going to building here this encoder layer and joining all of them. And after that, you're going to building here this decoder layer as well. Now let's fight first, try to creating here this encoder layer. And if I see this one, you have one multi-hat attentions. We have the at and norm is nothing but on skip connections. Then we have the query, key, and value. And if I simplify this one, we have also scaled that product. And I already imported, actually implemented those things in our multi-hat attentions. Now we're going to creating here a class that's called the uh, encoder layer. Okay, here you have the input embedding as well as you have the positional encoding, right? But better we can actually simply going to first building this layer, and after that you can joining this out in the transformer scale, right? Now let's start to building this block, and after that you're going to joining this all of the things. Okay. Okay, so let's create a class called encoder layer. Let's say encoder layer, which can same inherit the nn.module, and after that we need to using here the same thing. Let's call def init underscore. Then you can passing here the self, the d model, and then you're going to passing here the number of heads. Then you're going to passing here the dff. Okay, then you have the dropout. Okay, because this is on deep learning technique as well, so you need to passing here the dropout to remove the overfit problems. Now I'm going to give it to the super, and inside that I can passing here the encoder layer. Let's call encoder layer, and after that I'm going to passing here the self, and then using here underscore init. Okay, that's it. Now we're simply going to do the initializations. First, we have the self attentions. If I see the encoder block, we have the first one self attentions. Then you have an feed forward network, also one skip connections. Then we have the at and norm, I mean normalizations one. And for this case, they're using here the layer normalizations, not the batch normalizations. If you want to know more that, you can go on Google and search for that. What is the difference between the batch normalizations and the layer normalizations? Okay, so I can initialize this one. Let's say first self attention. Let's say self attention is equal to, I'm going to using here the class that you create, that's called the multi-hat attention, and which I'm taking the d model, and then it will taking the number of hat. Okay, that's the number of hats. If I go up, you can see here this is called the multi-hat attention that you can see on here, right? So you're going to just initialize this one in the from of self attention variable, and then after that I'm going to passing here the d model, the number of hats. We have the self dot the feed forward network. Okay, feed forward network. Okay, you have the feed forward network that is nothing but inside our encoder layer. So we have the positional encoding. Let's say positions wise feed forward, position wise feed forward. Then I'm going to pass it to here. We will taking the d model and the dff. Dff is nothing but called the feed forward network. For the dimension of that is nothing but 2048. It's mentioned in the paper. Then what you have, we have the norm one. Let's say self dot norm one, and it should be the nn dot layer normalizations. It should be layer norm, and I'm going to pass it here the d model. It's just taking the d model as a layer normalizations. Then you have the norm 2. If I see the architecture of encoder layer again, just need to click on here, and then you can see that we have an add to a norm. We have just one feed forward layer. We have the two add and norm. So you need to initialize the two norm layer normalization for that. So I can go on here, and I'm going to taking the next one. That's called norm 2. Okay, that's a norm 2. So it should be nn dot layer norm, and inside there you can passing here the d model itself. Then I'm going to add here the dropout. Let's say dropout. Okay, dropout, and then I'm going to adding here nn dot dropout. Okay, and inside there you can passing here the dropout ratio as a variable. Now we have all of the initializations is cleared. Now you can simply go to define here our forward pass. Let's say forward, I mean our forward method. So this forward method taking one self and x and marks itself. Okay, so why marks c? Because this is an encoder layer, marks is not applied, but you need to passing this out as argument because it's taking as argument while creating here the multi-hat attentions. Okay, in the encoder layer we don't have any marks multi-hat attention, so you can make it as none. So first what we have, we need to passing this x data in the multi-hat attention, I mean our self attention. So in our self attention you can pass it as a q, k and b. It's nothing but my value for that. Okay, this x is nothing but the q, k and b, I mean query, key and value. So you can pass it as a multi-hat attention as well. So that's our d model. So you can pass in, let's say self attention, let's say self attention, and you can pass in let's say x comma x comma x, and then you can pass in here the marks itself. Okay, now this is nothing but my attention output of my self attention output. Let's say attention output, and after that we can simply go into add it to our norm. Okay, add it to our layer normalizations. So in here what I can do is simply going to adding here one dropout with the self attention. It's called at and norm. If I go on here, you can see here we have this at and norm. See, we have at and norm, and we have also connection from here. Okay, skip connection, that's mean this is nothing but coming as x. Okay, we can join them, after that we apply here the normalizations. See, at and norm. Okay, at and norm. So what I can do, you can simply go to joining them with the query of that with the attention output is coming from here. Okay, attention output is coming from here. That's mean it will adding this from here also, this multi-hat attention as well. So how can you implementing this one? We can simply going to say that we are going to pass it inside a dropout first. Dropout, that's our attention score. Okay, that's our attention score, I mean attention output, sorry, attention output, this output, and then we're simply going to add it with our, okay, add with, and then you apply here the normalization. See, we give it here the output of the attentions, and you also add it them. Okay, this is coming from here because x itself is nothing but a query key and value. So you can simply go into using here self dot norm one. Okay, let's say self dot norm, oh it should be norm one. Okay, now you can simply go into remove closing this out, and then it's nothing but our x itself. Okay, that's our first one. Now we're adding here the feed forward network. It's actually defined, this actually it's mentioned in the paper. So and you're using here self dot feed forward network. Okay, that's our feed forward network, and inside there you can passing here the x. Then we can simply go to take it, let's ff. It's nothing but our feed forward network. Now this feed forward network again going inside our encoder layer. Okay, if I see on here, you can see here it's not going inside here. This one it having a skip connection, as well as the feed forward network is passing through the at and norm. So what you can do, you can so go in this thing in the same way. We can, let's say x equal to self dot norm2, and inside that you can passing the x plus self of, see, self of dropout, we can passing with dropout, and inside that you can passing here our ff output. Okay, this is nothing but is passing our feed forward network. Now we can returning the x. This is nothing but our encoder block. Okay, let's say return the x. See, so what we do here, first you're going to mentioning here the multi-hat attentions, then you have the position wise feed forward, then you have the layer now, we have the layer now, we have the dropout, and you're creating the forward pass. Just to creating here the block of the layer. Okay, not you're not going to creating here the whole transformer. While you're going to create the transformer, you can adding here the position and embedding as well as the input embedding as well. Okay, now what I can do is simply going to designing the next one that's called a decoder layer. Now if I go on the paper again, okay, so you can see here, this is nothing but the decoder block. In the decoder, we have the mux multi-hat attentions, as well as it having at and norm in 3 times, see 3 times, okay. Also having the feed forward network, also have the multi-hat attentions, also have one cross attention. You can see here, key and the value is nothing but coming on here, okay. Cross attention is nothing but coming on here, okay. We're also implementing this one. This is nothing but coming from the encoder block. See, coming from the encoder block as the output, or the as the output of this one, output of the encoder block is coming as the input of the decoder block. You can see it's called the cross attention. See, cross attention. Okay, because it's also one type of multi-head attention, but it is following here this cross attentions. And also because we're going to building this transformer for the language translation, we have the source marks as well as we have the target marks, right? Now what I can do is simply going to creating here a class called the decoder layer. See, we're just going to designing this layer, not we are not designing this output embedding of the position encoding in one single block. Okay, we're just going to creating this layer, and after that we can simply going to building this full transformer architecture, okay, in another class called the transformer. Now we're simply going to creating the class called the decoder layer. Okay, let's running this out first. Then after that we can create in the class called decoder layer. Let's say class decoder layer, and then I'm simply going to using here nn.module. Okay, we can simply go to using def, let's say init, and then inside that you can passing here the self, the d model, the number of head. Okay, number of head, it should be number of heads like that, number of heads. Then you into passing here the dff because you have the feed forward network as well. Then you have the dropout. Okay, fine. Now let's creating here the super constructor. We can passing here the decoder layer. So let's say decoder layer, and inside there you can passing here our self and dot underscore underscore init. Okay, now you can simply going to using here the same thing. Let's say self dot, okay, you can taking one shell or space, it should be better. Let's say self attention. We have the self attention is nothing but called a multi-hat attention, and inside there you can passing here the d model and the number of head, okay, number of heads. Then you have the another attention called the cross attention that you see on here. Key and the bill is coming from the encoder layer. Okay, so it is called the cross attention. Let's say cross attention. Then you have the multi-hat attention. Let's say multi-hat attentions, and because this is one time to multi-hat attention as well, which I'm just having in the marks. Okay, let's say D model, and then you have the number of hats. Okay, let's say number of hats. It should be number of hats. Okay, hats like that. And after that, what do you have? We have the self dot feed forward. Okay, let's say feed forward. We have just one feed forward network inside our decoder layer. We can use it, let's say position wise, position wise, feed forward, and inside that you can passing the D model and the DFF. That's a DFF. Then you have the three normalization layer. Let's say self dot norm one is equal to nn dot layer norm, and inside that you can passing the D model itself. And then we can simply going to copy this out the multiple time or three time because we have the three layer, okay, not layer normalizations, 2 and the 3. Okay, it will calculate the gamma and the beta value is nothing but in the form of layer in layer wise, so that's called the layer normalizations, which shortcut, right? Now we can add in here the dropout. Let's say dropout is equal to nn dot dropout, and inside that you can passing here the dropout itself. Let's say dropout. Now we're simply going to creating here our forward pass. Let's say forward is same as well as actually nothing but for the encoder layer as well. But in encoder we don't have any source and the target box. Okay, because in the decoder layer all of the translation is actually happening. It's nothing but an output block. So we have the self, we have the x, we have the marks, that we have the source marks. See, we have the source marks and the target marks. The source marks and the target marks is nothing but using in the decoder layer for the cross attentions. So now what I can do is simply going to creating this one, and after that you can simply go into using these source marks and the target marks is nothing but for doing the translation of that. Now what I can do is simply going to creating here our forward method. We have the attention output. Let's say attention output. So first one is called the self attention. Let's say self attention. So let's say self attention, and inside that you can passing here the x comma x comma x and our target marks. See, t target marks. That's our target marks. It's passing as a self attention input. Okay, because this is an mux multi-hat attentions. We have to passing here the marks itself. Okay, then after that what I can do is simply going to doing the same tracks that we do in the encoder layer. We have the at and norm, also one have a skip connection on here, I mean the residual connection. So we can using here x equal to c self of norm one and you can passing here the x plus self of dropout into passing it inside the dropout. Then inside there you can adding here the attention output. Okay, attention output. Now after that, what do you have? We have one cross attention. If I go on here, we have one cross attention. You can see we have one cross attentions. Now we're going to using this one to this multi-head attention mechanism that attends to the encoder output. It's nothing but the encoder output is passing as a decoder input. Okay. So now what I can do is simply going to actually creating this out. So while actually creating a transformer that you can know it more clearly, because you need to adding this out. Now we're simply going to adding here our next layer that's called the cross attention. Let's say cross attention, because it is crossing, it is taking the output from the encoder layer, and inside that you can passing here the x, and to passing here the encoder output. Let's say enc output. When you're also passing here one more thing, instead of marks it should be the encoder output. Okay, it should be encoder output. It's enc output. That's my mistake actually. Okay, encoder output, because this is output is coming from the encoder layer. So you can pass in here the encoder output. Okay, see why? See, because if I see that it's called query key and the value. Now we have the query key is the encoder output, and also the value is also the encoder output. See how we creating here the cross attentions. Then you have the source marks. We have the source marks. We have the source marks, not the target marks. Target marks is nothing but for our targeting marks of our input. Let's say I'm going to using here a sentence. Let's say hello, how are you? Okay, let's say hello, how are you? Okay, let's just say how are you? Okay, if I translate it in Bengali, tumi kemon acho. Let's say tumi kemon acho, kemon acho, like that. In Hindi, tum kaise ho? Okay, let's say tum kaise ho. Okay, it should be the H double N hun. Okay, tum kaise ho? Bas. Tumi kemon acho? Tum kaise ho? See, this is nothing but my input. It's nothing but coming as the encoder layer, and in the decoder layer we have tumi kemon acho. Okay, that's my target class, because we're just following here as supervised machine learning problems. So based on that, because this is my output is coming from our encoder layer into passing this one inside our decoder layer, so that it can calculate the loss of that. Okay, so that's why in the cross attention to passing here, the encoder output is coming from the key. Encoder layer is nothing but our key and the value, and we have the source marks. I mean source marks, and target marks is directly passing to our multi-hat marks, multi-hat attentions, so that it cannot see the last one. Okay, it can see the last one and it will try to predict them. Okay, otherwise our model should be the overfit problem. Okay, you can go on the Google again, search for the cross attentions if you want to know more about that. So this is nothing but our attention output. It should be the attention output. Okay, then what we have the next one, self dot norm2, to passing it inside the norm2. So you can pass in, let's say x, and you have plus self dot dropout, and inside that you can adding here same thing called attention output, and then we're simply going to pass it inside our x again, and then you have the feed forward network, just like the encoder layer. We have the feed forward output, and you can using here self dot feed forward, and then inside there you can passing here the x, and then you can using here x equal to same thing self dot norm3, and passing here x plus self dot dropout of the ff output. Okay, let's say out. Okay, it should be the put output, and then we're simply going to returning here this x. Okay, that's it. Now you can running this out, and this is our decoder layer. Now what I can do is simply going to building the transformer architectures. Okay, so for that you need to go on the paper again. Let's go to the paper. Now we're going to building the transformer architectures, because you're already defining here the encoder layer, decoder layer, and also building here the building block, just like the multi-hat attentions, position wise feed forward network, as well as the position encoding. Now we're simply going to building this full architecture. So what we have the input embedding. which are passing through as a input. Then you have the positional encoding. Then you're already creating this layer and to joining these cross attentions. And you have the decoder layer. We have the position encoding. We have the output embedding, as well as we have the linear and the softmax. Then you can got the output probabilities, right? Now I'm simply going to implementing this one. One more thing, you can see it's called and cross. Okay, and cross, number of head. I mean, sorry, number of nodes, number of head. Number of head is nothing but 8. It's nothing but called the identical layer. I mean, that's mean how many layer it should be present in our encoder and decoder block. See, it's just having one layer, but not just one layer. It's nothing but a stacked encoder the decoder. It will pass into the data to the one layer to the another layer and give me the translations of the language. Now let's create the class called the transformer. So let's say create the class called transformer. Okay, transformer. And inside that you can passing here nn.module, and then we need to defining here init, and inside that I'm going to passing here the self. Then I'm going to passing here the source. Okay, source bookab size. Okay, that's our bookability size of that. Then you have the target bookab size. Okay, let's say bookab size. That's our bookability size of the target variables. Then you have the D model. Then you have the number of heads. Let's say number of heads. Then we have the number of layers. How many layers we have in terms of feed forward network. Then you have the DFF. That's nothing but our feed forward network. Then you have the max sequence length. This is nothing but a sequence of the sentence. Let's say sequence length. Then we have the dropout. Okay, so those are nothing but the properties for the transformer. Now we can simply go into creating here the super. So let's say super, and inside that you can passing here the transformer. Let's say transformer. Okay, we can simply go into add it and adding here the self and underscore init. That's it. Okay, now we're simply going to creating here our encoder embedding, because into passing here the input embedding for the both actually encoder and the decoder. So this is nothing but the initialization part. So we're going to actually designing here our input embedding for the encoder and the decoder layer as well. I mean encoder the decoder block. So you can using here, let's say self dot encoder embedding. Okay, let's say encoder embedding. Then you can simply go to using here nn.embedding. Okay, because we already have it inside our neural network module in the PyTorch. Okay, in the embedding, I'm going to passing here the source bookab size. You have to pass in the source bookab size, as well as you need to passing here the D model. Okay, that's our input embedding of that. Now after that, what I can do is simply going to give it here decoder. Let's say self dot decoder layer. Let's say decoder, and you have the embedding. That's embedding, and then you're going to using here nn dot embedding, and then inside that you can pass in here target bookab size. Okay, bookab size, and then you're going to pass in here the D model. So why this target bookab size and the source bookab size? If I do the language translation using this transformer, the bookab size of the target size and the source size can map the different. Okay, so that's why we're going to passing here the target bookab size and the source bookab size. I mean the bookability size. And we also passing here our D model. Okay, the dimension of the models. Now after that, we need to actually using here, I mean initialize here our positional encoding. Let's say positional encoding. Okay, let's say encoding. The make sure that while you're doing the transformer coding, your architecture should be in front of you, because in my case the transformer architecture is nothing but in front of me. So that's why I'm just going to think this one, and I can building the uh, I can build in this one from the scratch. Okay, we have the positional encoding. Now we can using here the positional encoding that you already created, which on taking the D model and the number of sequence, and our number of sequence is the max sequence length, this one. Now we have the self attention. Now you can defining here the encoder layer as well as the decoder layer. You already implementing this one. That's self dot encoder layer. Okay, encoder layers. Now because we have the stacked up, we have the stacked up the encoder layer or the encoder block. This is nothing but one module list. We can simply going to create a module for that. And for this case, we have the 6 identical layer of the encoder block. So you can using here nn dot module list, because this is nothing but stacked encoder, and inside that we can passing here our encoder layer. Let's encoder layer, and our encoder layer is nothing but taking the D model and the number of heads. Let's say number of heads, and also taking the DFF and the dropout. Let's say dropout. Now we can simply go into iterate to all of the value or the number of head. For that we can using here insert and list comprehension. Let's say for I in range, and we can simply go to passing here number of heads is nothing, I mean number of layers is nothing but coming as a parameter in our transformer. Okay, so this is nothing but our encoder layer, and you can simply going to copy this out, and then you can simply go into pasting it here. So this is nothing but for the decoder layer. You can making it decoder. Okay, let's say decoder layer, and instead of actually using here this encoder layer, we can using the decoder layer itself. Now we have the encoder layer and we have the decoder layer. Then finally you have one Boolean layer as well as one softmax activation functions in our transformer. So you can using here as a self dot fc as called fully connected layer, or the linear layer, that's nn dot linear, and you can passing here the D model and our target bookup size. It's a target bookup size. It should be target bookup size, and then I'm going to using the dropout. Let's say self dot dropout. Dropout is equal to nn dot dropout, and you can simply going to pass it the dropout inside that. Okay, this is nothing but the initializations of our transformer. Now we can simply go into creating here a function that's called the generate marks. Okay, generate marks is nothing important, just because of to passing as a source and the destinations as a marks, while actually do the cross attentions, as well as in the decoder block we have the mux multi-height attentions. So we're also implementing these generate marks functions. So the generated marks function is nothing but taking one source as well as one target. It's better we can go on the presentation slide and understand this one, what are the marks it's actually working on in the case of transformer. Then we can simply go to code it out. What is the mux multi-head attentions? Because you need to also using here functions to generate the mux for the decoder layer. Now if I see this, the mux multi-head attention is nothing but one kind of attentions which are using the mux. Our goal is to make the model casuals. It's mean the output at certain positions can only be depend on the word on the previous positions. Let's say I'll give you an example. Let's say call how are you. See, we have the sequence. Okay, we have to follow the sequence. How के बाद R आएगा, R के बाद U आएगा, how के बाद U नहीं आएगा. Like, so you need to also follow the positions of the each of the words so that you can do the language translations, as well as the model must not be able to see the feature word. Otherwise, our model is running into the overfitted problem. Okay, it will face a overfitted problem. It will just work in the training data well, but it will not working in the testing data well. That's called the overfitted problem. In the training data, it will working perfectly, but in the new data is coming out, it's not perfect well. Okay. If I see one example, I love you in every universe, and you can see here, I love you in every universe in the y directions. See, while I'm going to generating here the I, we have all of our positional encoding value, but all of the value you can see here, the love you in every universe is cross, or it will actually replace with the minus infinity. Those value you can see here, those value is nothing but cross, and it will actually actually invert it into or fill up with the infinite value. Okay, this is called marks. As well as you can see here, the marks is nothing but following the diagonal space. You can say diagonal space. If the love is generated, the all of the rest of the four value is nothing but the infinity. Okay, that's mean our word not able to see the feature word. It will generating this one, and based on that we can calculate the loss of that, and we can do the optimization technique. Okay, so see for the U, same, it will generating last time the U, and it will not generating this one marks. Now this is called the marks multi-hat attentions. Further to creating here marks which are taking one diagonal, which are having on trie as well. Now we can simply go into actually creating the functions called the generator marks, and you can passing it inside our decoder layer, because in the decoder block we have the marks multi-hat attentions. Now we can define the functions called def generate. Let's say generate marks, and which one having the self, and we also have the source and the destination. Let's say source, and you have the marks. Now what we have the source marks. So let's say source let's say marks is nothing but, so source is nothing but, let's say if the source is not equal to 0, and you can simply go down sequence with the 1 and the 2. Okay, 1 and the 2. So let's say unsequence. So let's say unsequence, and then we can using unsequence of the 1, and also you're going to unsequence, let's un as q u e e z unsequence in the from of 2. Okay, this is nothing but my source marks, I mean in the x and y format. Then you have the target marks, we have the target marks, and target marks is same thing if the target is not equal to 0. Okay, and then you can simply go to unsequence it, let's say unsequence it of the 1 2 3. Okay, let's say same unsequence of 3. Okay, we have the source marks and the target marks. Now what I can go, we simply going to creating here one peak or the no peak, because we have one diagonal format. If I going to calculate the diagonal of the marks, and if I removing these from our whole matrix the marks one, we can simply going to getting here our peak value. Okay, so for that you also taking the sequence length, that's a sequence length, it's a sequence underscore length, and you can using it, let's say target dot size, because based on the target it will creating the marks for that. Okay, if I have the target call I love you in every, let's say it actually just going to printing here the I love just like that, and you in every universe is nothing but in the form of marks. So how can you calculate them? We have to calculate the sequence length for that, and after that we can removing the source marks to the destination marks. Okay, I mean our target marks. So for that we can take in one variable called no peak, let's say no peak marks, which one don't have the marks. So you can simply going to remove it from the 1, because I just taking as a 1 as a full value for that, and you can using here torch.trio, because this is nothing but a diagonal types of things. So you can using here trio, and inside that you can passing here torch.ones, that's a torch.ones of 1 comma sequence length, see sequence length, and then you can simply go to using here the sequence length itself, that's a sequence length. Okay, then it's simply going to giving the diagonal equal to true. Okay, I mean diagonal equal to 1, so diagonal equal to 1, and then inside that I'm going to passing it as a bool. Okay, bool real variable. Then after that we can simply go into do the metric multiplications for that, for the target marks and the no peak marks. So that's our target marks, and after that you can do the matrix multiplication, you can use it this one, and you can using here no peak marks, let's say no peak underscore marks, that's our target marks itself. So that's our target marks. This is how we can generate the marks for each of the sentences. Okay, so we can returning here, let's say return here the source marks and the target marks. Okay, now it's simply going to creating here a forward method, because our generate marks is also important. Let's say def forward, and we can simply go to taking the self of the source and the target, let's say target. Now you can simply go into using here source marks, let's say source marks is equal to source marks comma target marks, because our generate marks should be called. So we can copy this out, generate marks, and inside that you can passing here the source and the destination, that's called our target. Now after that you can simply go into passing here our source embedding, so you can using here source embedded. Okay, and our source embedded is nothing but our positional encoding, and passing it inside our input embedding. I mean that's mean we have our self dot encoder embedding, that's an encoder embedding, and inside this encoder embedding you can passing here the source. If I see the architecture of the transformer again, then you can see it understand clearly. You have the output embedding, and output embedding is passing inside a positional encoding, as well as the source embedding is passing as a positional encoding. That's when you need to defining the position encoding first, and after that inside that you can passing the source, and inside that you can simply go to passing here inside it our positional encoding. We can, let's say positional encoding, and now after that you can simply go to passing it inside a dropout, because we already initialize here a dropout as well. That's a self dot dropout, and then our source embedding is created. Okay, then after that we have the target embedding, so let's say tgt embedding, let's say embedded, let's say embedded. This is nothing but our the for the output embedding, so this is nothing but the same as well, but just it will taking the target itself to passing the source and target in the same positions. So dropout, self positional encoding, self decoder embedding. So that's a decoder embedding, and inside there to passing here the target itself. That's a target. Okay, so we have our target embedding. Now we can actually using here the layer of that, because we have the 6th layer. So you can simply going to use it for the encoder layer. How many encoder layer we have, because it is passing through from here this encoder layer, and we have the 6th encoder layer is the number of layer. Okay, so we can creating here a for loop. So let's say for, okay, for let's say encoder layer. Let's say encoder layer in self dot encoder layer. Let's say encoder layers. Let's say encoder layers, because in the encoder layers block that you created on here, it has a sys list. That's when you toss iter to all the bin from here, and after that you can simply go into store it inside a list. Okay, so what I can do, we can, let's say encoder output. First we're going to passing here our source embedding. Okay, this is nothing but source embedding is nothing but our embedding of our word, that is nothing but as a source. Okay, now that's our embedding output, I mean encoder output. We can append it, we can using here source output equals to encoder layer. This is our encoder layer, and you can pass in here the encoder output and the source marks. Okay, it should be the encoder output and the source marks, because in the encoder layer we have the 6th layer stacked. So you can simply going to add it to all the layer from the encoder layer, and you can simply going to add it inside our encoder layer, each of the encoder layer as a encoder output and the source marks. Okay, and after that what I can do is simply going to do the same thing for the decoder layer as well, because this is a stacked one after encoder layer, we have one after encoder layer, and this output should be passing to the next of the encoder layer, and those outputs should be passing to the another encoder layer. So that's why creating here this for loop. So to do the same thing for the decoder as well, so you can copy this out, just going to changing the variable name. So you can go on here, and instead of the encoder output, you can using as a decoder output. So let's say decoder output, that's a DEC, and instead of using the source embedding, you need to using here the target embedding, and this one should be the decoder layers, and then this one should be the decoder layer. Let's say decoder layer. Now decoder layer should be passing on here, and this output should be 4 times, because when to passing here the decoder output, if I see the decoder layer, we have the D model, we have the number of head and the DFF as a dropout, and inside that forward pass we have the X, and X is nothing but the output. We have the encoder output, as well as you have the source marks and the target marks. So you can passing through on here. So what I can do, you can simply go into making as a decoder output first, then you can simply go into first passing here the decoder output, then you have the encoder output, we have the encoder output, because you're passing as the encoder output in our decoder block, then you have the source marks, and you have the target marks. Cool. Now we can simply going to pass it inside our fully connected layer. So what I can do is simply going to return output. You can give the output, let's say output equal to self.fc, and inside that you can pass in here the decoder output. That's our decoder output. Then you can simply go to returning here the output here now. Okay, output. Okay, that's it. Now you can simply go into running this out, and after that we can got in here our transformer. Okay, so you can got our transformer, so we can simply go to removing this out, and you can running this out. So that's our transformer. Now let's try to testing this transformer with some kind of example value for the source vocabulary as well as the target vocabulary. So I am simply going to initialize all the value for the source, target, D model, number of head, number of layer, DFF, max length, as well as the dropout. Okay, also I revised the full code just because of the Jupyter notebook don't give me the warning error. So I actually mistaking this one. Let's call output. It should be the output. And I also doing some mistake on here in order to actually calling the functions scale dot product. I don't adding here the self, and also I do one mistake on here while actually passing here the attention scores. And those are the simple kind of mistake I actually do while do the coding, because it's a human error. Okay, now what I can do, I am simply going to define here the source vocabulary, the target vocabulary, D model as well, and also you can see here I also changing the output as well. Okay, now I am simply going to add here the source vocab size. It's nothing but the 5,000. I just taking it as an example, Then you have the target bookkeep size. Let's say bookkeep size is nothing but the 5,000. And then we have the D model is our D model. So you have a D model, and in paper they mention the D model size is nothing but the 512. This is the vector size of the D model. Then you have the number of heads. Let's say number of heads. So number of heads is nothing but six. It's mentioned in the paper. You can also increase the number of head as per your problem statement. Then you can add in here the number of layers. Let's say number of layers is nothing but the eight. And then okay, number of head is nothing but sorry eight, and numbers layers is nothing but the six. Okay, layers is nothing but the layers of the encoder and the decoder layer. It's mentioned in the paper is the six, and number of hat is nothing but six. It's nothing but a split hat. While after going to do it in the multi hat attentions, then you have the DFF is for the feed forward network. The input layer is nothing but called 2048. It's nothing but the hidden layer. Sorry, hidden layer input is nothing but called 2048. Then you have the max sequence length. Let's say max sequence length, and max sequence length is nothing but let's say 100. Then you can taking the dropout. Let's say dropout is let's say 10% of the dropout. Now I'm simply going to define here the transformer. So I can using here the transformer, and then inside that I can passing here all of my value called the source bookkeep size, target bookkeep size, D model, number of head, the number of layer, DFF, the sequence length, and the dropout. We can pass it to here, and after that we can store it inside a variable called transformer. Okay, transformer. Okay, let's say former. Let's running this out, and it will execute it, and then you can simply going to see this one. Okay, so this is the architecture of our encoder and the decoder. I mean our full transformer. We have the encoder embedding is called 512. It's nothing but my D model, and the 5,000 is nothing but my bookability size of the source, and the decoder embedding. And you have the positional embedding. We have the encoder layer. We have the six layer itself: 0, 1, 2, 3, 4, and the 5, starting from the 0. And each layer is passing as an input to the next layer. Then you have the decoder layer as well. You can see decoder layer. We have one. We also have the cross attention. You can see here, cross attentions is nothing but coming from the encoder output as a decoder input. Okay, and also you have the cross attention, feed forward, all of the things we have. Okay, now what I can do, we simply going to using this transformer to generate some random sample data, and after that you can do the testing this out. So for this case I'm going to using the Google Colab just because of uh, if I can't run it here, I cannot run it here in my own machine because I don't have this much more amount of GPU as well as the coda. So obviously it will actually start it my full system. That's why I'm going to using here the Google Colab for training this out. Okay, just for checking that how we training the inference of the transformer model. Okay, I upload the whole code in the Google Colab, and you can see all of the module, our multi-head attentions. Then you have the positional voice feed forward network and the positional encoding, and you have the encoder layer, decoder layer, transformer itself. Then you have the testing one that's called transformer. Now we're simply going to generate some of the testing data. You can see here we have the source data. We generate it using some random variable data. You can also using here the sequence of one sentence. So you have the random towards your reindeer, and it's simply going to uh, actually uh, actually generate it based on the sequence length. You have our source data and the target data. Then we have the citration is nothing but uh, for the cross entropy loss. We're going to using it here, and after that you have the optimizer to optimize the whole of the process, because we have the it's nothing but our neural network itself. We have the forward pass and the backward pass itself. Then you're going to using the transformer that train, and inside that you can passing here the 100 epochs. So let's making it as a 2 epochs. Just I'm going to checking this one, and I'm going to making this optimizer is a 0 get. I'm just making it a 0 get, and after that I'm going to using here this transformer. That's our transformer, and inside that you can passing here the source data and the target data. Also one more thing, while I'm doing the coding, I also do one mistake in the generated marks. If I go on here, you can see in the code of the Jupyter notebook, I actually using it as a marks. I just replace this as a target because it's my mistake to actually type it quickly. So that's why I just unfortunately I give it here the marks itself. You need to convert them into the target, and then your code will work perfectly. Okay, then you have the target data, and then you can add in all of the target data from our target variable. That is simply going to calculate the loss, and using the loss or backward to do the backward propagation, and also using the optimizer step so that it can optimize of the each of the step of the epochs. Okay, then you're simply going to calculate the transformer dot evolutions, and we're simply going to see the validation loss as well. And just because for the understanding, I just simply going to add it here, some of the input. Okay, this is nothing but for the training, and after that you can do some validations with those data. So what I can do, I am simply going to running this out for checking that our transformer is working really perfect or not. And we are going to running it for the two epochs, and it will check in the validation score as well. So you got some error. Argument size failed to unpack the object of position 2. So we have some error in these sections. Now let's see what kind of error we got while do the coding for the generate marks. This error is coming from this generate marks. Let's check in this one. Yeah, in the target size, you need to also specify here the size of the sequence layer, so you can pass in here the first index of that for the ones. So that's why this problem. So you can running this out. Let's try to running this out, and now let's waiting for this one. It is working or not. Okay. Yeah, this kind of few mistake can be happening because I am not a robot at all. I'm a human. It's also be happen. Okay, so let's waiting for a few seconds and let try to checking that that our epoch is started or not. You can see here we have the two epochs. I just give it here for the testing purposes, just for ensure that our loss is decreases, because in the terms of the NLP of the deep learning is nothing but calculate the loss and decrease the loss for that. Okay, and you can see that it's starting. I hope so. Yeah, it's taking time. I'll back right after when it is started, as well as it's also completed, because it will taking really much more amount of GPU in the Google Colab itself. If I'm running this one in my own system, it will be crashed. You can see here epochs 1 loss is nothing but 8.69. Okay, let's wait for the second epoch, and as well as for the validations. Okay, because in the validation is the same thing. It just calculated in the citations. In the citations, we actually using here the cross entropy loss. So in this case, we can actually calculate the loss of that. Okay. Okay, so our code is executed, and you can see here it will actually decreasing the loss for the each of the epoch. We have the loss is 8.69, and in the second epoch we have the loss of 8.54, and our validation loss is 8.65. That's mean our loss is decreases. Okay, so this is how the transformer is actually work, and how can you use the transformer in kind of language translation, but you're not actually using it for the language translation yet. But if I got more responses in this transformer architectures from the coding, and I am simply going to implementing this full architecture model in the language translation as well. So that's it for today now, and hope you enjoy this full tutorial, and make sure to subscribe to the channels and share with your friends, so that it's actually giving the motivations to making this kind of cool projects, and the so not cool projects, actually cool concepts in the form of deep learning and the natural language processing. So thank you and bye bye.